So my name is Juan Garay. I work in cryptography, cryptographic protocols, some distributed computing, and I joined work with Ron Cohen and Vasily Zikas, Reichman University, and Vasily just moving to Georgia Tech. And I should warn you that the slides are very nice because Ron made them. And I'm still trying to figure out what they say, but we'll do it together. I'm joking or not. All right, and I was hoping in the original program, Abraham was going to talk about adaptive security. So I was hoping that he would do a little background for me, but things
There was
change,
some security issue, that's why I'm not here.
like cancel flights or something.
Yeah, flights were canceled.
So I added a couple of slides to get you into the topic. So and this is an academic paper, trying to prove bounds of what can and cannot be done in theory. So the topic is adaptive security, the setting, and where there's an adaptive adversary who's is going to be able to take over parties, players on the run. All right, so depending on what the situation is on the execution and what she sees. All right, and so the adaptive security would be you try to come up with something that is secure against this type of adversary and achieves its specification, right? Which we're going to get back to because there are different ways of how to model this problem, right? Adaptive security. So why do we do this? Well, it's in crypto, we've been doing this for a while. But one of the more recent motivations is the situation where you're trying to scale consensus. All right, classical consensus, big, large number of nodes, and therefore inefficient, and so forth. And then you would like an oracle, and I'm going to query Thomas. Thomas, recognize this picture?
I don't know the lady, I'm sorry.
It's a hint is in Delphi. It's an oracle, right? And what was the name of the priestess?
Yeah.
All right. I would have said Pythia, but Pythia. All right. So the point here is that somehow, you're going to get a way to distinguish a subset that are going to do things for us, right? And the subset is going to be smaller, right? Little o n, where n is total number, the size of the network, and everybody's going to try to figure out what this small subset did. All right, so these guys are going to work to try to achieve consensus by themselves, and then they're going to spread it out. All right, and the point for this is that if assuming these bounds, then the corruption thresholds are maintained, and then you can assume that if the committee achieves consensus, then under enormous majority overall, then this is going to work, plus or minus, right? And this is what some of the Byzantine fault-tolerant approaches to blockchains would do. All right, and I mentioned this. So protocol is going to be secure if it achieves specification. What do we mean by that? And now we get into the crypto aspect of how to define security. All right, de facto popular way of defining security these days for cryptographic protocols is called the simulation paradigm. All right, and we'll see what that is. All right, and on the right, we have the protocol being run in the real network and with a real world adversary, okay, that corrupts parties, and then the protocol takes place. Okay, and we are going to say that something is secure if there is an ideal specification, an ideal way of doing it. See, this is the trusted third party type thing that does the computation. All right, there's a real world adversary called the simulator. Okay, if that guy corrupted these guys, right? So this simulator, the ideal world adversary is going to take over these parties, but this is an ideal execution, right? So inputs go to the trusted party, outputs come out, okay? And we say that this protocol on the right is going to be secure if its execution, which is defined in a suitable way, between the two worlds is indistinguishable to this part here, to distinguisher, environment, and so forth. All right, ideal world, real world. Again, this is called the simulation-based simulation paradigm, real ideal paradigm. Okay. So what do we do in the case where corruptions are adaptive? Okay, in this case, notice that this guy corrupted these two parties before the execution started. All right, so in the adaptive case, the animation should reflect that. See, the protocol started executing, then there is a party got corrupted, got taken over by the adversary. Over here, more executions, and then the guy corrupts some other party and so forth. Okay, and then this specification should say that now these two worlds and the execution of these two things are indistinguishable. Okay, and why do we do this simulation thing? Because it captures in one shot, supposedly, ideally, captures everything we want to say about the ideal specification of the protocol. It supports composition, meaning that you're able to run one protocol call from another protocol, and if you prove them secure in this way, right, then the whole thing is going to be secure. You don't have to reprove the whole thing from scratch, which is very important. Supposedly has a very clear meaning of security, especially if you're able to specify a task, very succinctly. However, it's it's not straightforward. It's hard to work with, and it might be in some cases an overkill, or not, but we'll see. Okay, so that's the simulation-based situation. And in contrast, we've been talking about these properties, right, that happen in distributed computing, definition of distributed computing problems, such as in the secure multi-party computation case, okay, can be stated as follows, right? So we want to do a computation tolerating an adversary, whatever to be defined, right? The computation produces the correct output. Private inputs are not leaked, all right? Inputs are and these are the other properties for MPC, independence of inputs, fairness, meaning that the adversary gets the output, then the honest party is connected to the output, and so forth. And guaranteed output delivery. Okay, this thing works and produces output. All right, that would be the property-based formulation of MPC. And now we want to talk about adaptive corruptions in this property-based manner. So this adversary is going to be adaptive. And then the basic question is, should a protocol, satisfying properties, okay, in the presence of adaptive adversary be considered adaptively secure? Okay, that was MPC, the more general formulation. And now let's look at adaptively secure broadcast, which is the subject of this talk. All right, which has as a goal, it means to simulate a broadcast channel, a megaphone, right? I speak, like now I'm speaking, everybody listens to me at the same time. And moreover, that everybody heard me and so forth. Okay, and it would traditionally, it's considered secure. So we have in this setting, we have a sender and we have receivers. That's a megaphone. And typically, the typical properties for this problem are agreement, meaning if means everybody is output the same value, And this is a more tricky situation. If the sender is honest, okay, and has input and broadcast is trying to broadcast X, then that should be the output. Okay, that's standard definition of broadcast or the Byzantine generals problem and so forth. And then the question is, would a broadcast protocol satisfying these definitions, the classical definitions, would be secure against an adaptive adversary? Okay. And it turns out that it's underspecified that it doesn't, because it's not clear if the sender is honest. We talked about when this was honest at the beginning, in the middle it got corrupted and so forth. All right, so we can try to play with that and see how that could improve. Right, we can say, well, everybody at the end of the protocol that was honest at the end of the protocol is agree on this value. And if the sender remain honest until the end, that will be the output. All right. So the question is, we added, enrich these two conditions. Is that enough? All right, and we'll see. We need something more. Is the situation clear so far? All right, we are dealing with adaptive adversaries, and we look at different ways of defining the problem for the case of broadcast, which is very related to consensus. And so let's see what happens when we have this type of situation. Now we have an example of a broadcast where you have a bunch of parties. Okay, and everybody wants to send a bit, and the adversary, for some reason, wants the output to be as close as possible to 0. Okay, so these are the inputs to these guys. It's using a megaphone over here, right? So this could be an execution, this situation. And here we have a case, all right? So this is the input values that the parties have. Let's see what happens when static corruptions. In static corruption, the adversary is going to corrupt parties at the beginning. Okay, and we're going to get this situation. Okay. All right, so he got lucky with this guy because he had the 1, corrupted this guy, he had the 1, and this was the output. All right, now what happens when we have an adaptive adversary? And a broadcast channel means it's the ideal specification. All right, it's going to go like this again. All right, because I'm assuming a broadcast channel, the idealized version. So let's see what happens now when we are trying to realize that functionality, the megaphone, using a protocol. All right, which pretty much follow this paradigm where the sender is going to send its input to every party. Okay, and then parties are going to try to reach agreement on the values that they received. Okay, that's the agreement protocol that taking place. All right, and these protocols then would satisfy agreement on validity should they be considered adaptively secure. And the point is that you saw how it started. The sender, right, sends value to the other parties try to reach agreement. It could be that the input, right, is first delivered to a corrupt party. And we call that a rushing adversary, right, that monitors what's happening in the network and then makes a move. Okay, so he learned the value X. All right, but he might not like the value X. So what it's going to do is it's going to jump in, corrupt the sender, right, and send some other value. All right, and that should, yeah. Okay, so we are in a situation where there was an adaptive corruption, and there are ways of one assumes different types of network assumptions to make sure that this operation may or may not be atomic, right? When somebody speaks, messages get delivered in certain order, and then there's the power of the adversary, whether it's going to be able to jump in after receiving the first message type thing. Okay, so we have this situation, and then what shall we do? Right, this seems to require strong adversarial power because, as I said, the adversary has to jump in, be quick, right, be the first to receive the message and so forth. And why do we care about this type of situation? Well, if we are going back to the blockchain motivation, right, everything goes over, gossiping, diffusion networks, right, where parties, it's not that all the miners, servers are connected to everybody, right, but they talk to, TCP/IP like gossiping way. All right, so that's the relevance. Okay, and if we have this standard broadcast protocol that is vulnerable to that type of attack, then we're going to have a situation like this. Okay. So we're in a worse. Yes, Fatma.
So are we aiming for a simulation-based instead of property-based proof?
Not yet. We're just talking about the protocol and the type of adversary is adaptive. Not yet. So we're going to see whether a simulation-based proof, can figure what do we need for this to be secure. But here we're trying to illustrate that pretty much any broadcast protocol that you run like this in this network model, right? The adversary is going to get the message first. It's going to corrupt the sender, and it's going to be a different message, which is what happened in this example.
So the UC model proof.
What's that?
The UC model proof. Like how
It's coming up. All right. Now the UC model, yes. I need the extension, right? These guys are asking questions.
I can also come back in here.
Oh, that's fine.
So in this example, the fact that the adversary should not be able to make the output close to the zero vector, it's not a property we initially sought for, right?
No, this is an example. So for some reason, the adversary wants to make everybody's broadcasting, right? So you have a bunch of, it's a made up example, right?
But is that something we are concerned about? Does that illustrate that?
Yeah. So, well, the adversary might not like, I'm broadcasting something. I don't like this stuff that you're saying. I'm gonna go, jump in, corrupt you, and make you say something else. So that should not happen. That's not captured by the original definitions, right? And the point is that you want to capture this dynamic, type of action where the adversary, figures something, doesn't like what you're saying, right? Jumps in and you want to. And in cryptographic protocols, this is like the type of adversary we like to prove security against. Adaptive adversaries, right? So why would the adversary corrupt in the beginning? Right, there's something going on, right? So it should be able to corrupt as the protocol executes. Adaptive security. Okay, Fatma, simulation you see coming up. All right, so it turns out that this observation, okay, that the adversary may jump in and change the guy's value, the sender's value, was pointed out by Hirt and Zikas, Eurocrypt 2010, all right, where you would like to see this, the ideal world pictures, right, the megaphone. You would like to prove a protocol secure in the simulation-based paradigm, all right? And turns out that you cannot, because what you can achieve is something called weak broadcast, which would tolerate this type of situation. Okay, that the adversary is able to corrupt the party and then make him change his mind, which is not clear that this thing shows. Probably not. But let me. All right. So all protocols would not do this, right? Will be vulnerable to this type of situation, where the adversary was able to jump in, change his mind. And these are the bounds that we know how to achieve this type of adaptive security. And these guys call it unfair megaphone. Okay, and we follow up and pick up the definition, but that means that the megaphone is not oblivious, right? Well, the guy started talking, right? It shouldn't depend, what the outcome is depending on what he's gonna say, right? So it should be like an oblivious megaphone type thing, right? The guy picks up the megaphone, speaks, right? And everybody gets that, as opposed to, pick up the megaphone, right? Start speaking and then changes his, then something else happened. All right, so it should be more like oblivious, but this guy's called unfair, so we're gonna follow up with the unfair type of terminology. But these bounds that you need to achieve this type of functionality, right, in the information theoretic setting, meaning no trusted setup, I got an extension, right? Right. It's N/3. Information theoretic, no setup. Okay, by no setup, I mean no PKI or some other stuff. Right. Now, if you assume a PKI, you can achieve broadcast for arbitrary number of corruptions. Yeah. I get 2 more minutes here.
Sorry. I think like more general, like this definition of security seems very, very strong. It wants the view to be indistinguishable between the real world and the ideal world. Why do we care about this indistinguishability? Like it could be that like we still solve broadcast, but the executions are distinguishable. Just the distribution over the outputs might be different in both cases.
Yes, yeah, in crypto, we like to talk about things that are certain except with negligible probability. And indistinguishability captures that. In crypto, you can relax that. So, well, if we're not doing crypto, I don't care. I want to be like half secure or something, right? Then I don't care. But this indistinguishability is not perfect, right? They're not identical, right? They deviate, but we follow the cryptographic approach, right? And say the difference between these two distributions are, they're not identical, but they're very close. That's okay, so those are the standard bounds, the traditional bounds. 2 more minutes.
Megaphone and unfair megaphone, I didn't get it.
I don't know what Rand meant here, but this has meaning. I think this has meaning later, which I want to get to. All right.
Yeah.
So we'll get to that. All right. If you do the ideal thing, the way you're supposed to do in a standard UC simulation-based formulation, you're gonna get, without trying to set up same bounds, but check out this weird bound that they got. All right, now we're talking about broadcast, PKI. Here you get arbitrary number of corruptions. Here you get not even T less than N/2, right? You get less equal N/2. That's kind of weird. All right, but you get different bounds. All right, and further, they show that it's impossible for dishonest majority. All right, and why is that, Fatma? All right, it's right. What's going to happen is that, right, the simulator here, when the execution starts, it's going to have to send a value to the functionality on behalf of the sender. This is the value the sender is going to send, right? But then the sender might get corrupted, and the simulator is stuck. It cannot change its mind afterwards, unless you do some other stuff. Okay, that's the basic idea. And looking at these weird bounds, then the people started wondering what's going on. Right? We like to prove things in the simulation paradigm, right? Simulation, composability supporting security. And maybe is this an artifact of simulation, the simulation paradigm? Okay, maybe we just do everything property based, then we can get away with stuff. All right, and this was there were a series of adaptive secure broadcast protocols along these lines. And another question that is promising, because this adaptive security happened in the setting of encryption, where somebody encrypts something, right, and then it gets corrupted, and you're trying to simulate that, right? Then if you want to prove that secure, you have to explain what the corrupted sender sent, right, what he was not uncorrupted, right? And then there's the notion of equivocation of these primitives. Okay, that gives us something called non-committing encryption. When I commit something, right, but if I get asked by subpoena, right, so what did you say? Well, I encrypted this stuff. I didn't mean that, or this is what I encrypted. Case deniability is one of the applications, right? And this is used with something that's called random oracle, the idealized version of a hash function, and the random oracle can be programmed. Okay, it's programmable random oracle. All right, and we'll be using that tool. And further, there is something that we use called, that was used in the past, called time log puzzles, and that had to do with, see the drop, the water coming out, that was the picture that's supposed to capture this. All right, and can we use TLPs to overcome this impossibility? And these are the main results. Okay, so this is what I just showed you. So Hirt and Zikas prove this. We show that property-based, you're also in trouble. You cannot prove it. All right. If you use a random oracle, you cannot do it either. Okay, and this is for a natural large class of protocols. And using TLPs, you can get the property-based version of the property formulation of the problem, but it doesn't help for simulation-based. While if you use, try to set up PKI, TLP plus a random oracle, programmable random oracle, you can. Okay, and let me give you an idea why TLPs help. All right, and this is something that, and we also have, now you're going to be using TLPs in the context of some other protocols. All right, and TLPs are, all right. So, okay, so this is resource-restricted cryptography where we don't go arbitrary polynomial time, but we are more concrete. The number of steps, number of exponentiation, number of operations, and so forth, to be defined. But this is what this is supposed to capture. And you say 2 minutes or 5 minutes? All right, so let me show you what we come up with a property that captures this deviation, right? You have everybody, if the adversary wants everybody to go to 0, it's going to go to 0. So we added a property that is called corruption fairness. Fairness in the sense that it's oblivious. You're going to corrupt independently of what the value is. All right, and this is what should be included to capture in a property-based manner, okay, an adaptively secure broadcast. Okay, so the two basic properties don't do it, and we show that you cannot do better than this. You cannot tolerate a majority or half the corruptions. Okay, and finally, what we do is, I want to say something about TLPs. So the idea behind TLPs is that the sender now is not going to send a value, right? But it's going to send, everybody is familiar with the time log puzzle? Let me put the time log puzzle here. Yeah, you have to do some work to get the output. And there are some additional properties that come with this. All right, but the idea is that if instead of sending a message, you send a time committed message using a TLP. All right, and then people have to work, and you have to relate that work with the number of rounds that the broadcast protocol is going to take. Okay, but it's hidden, so the TLP is hidden, right? So the adversary would not know what the value is to be able to jump in and corrupt the sender. All right, and so this is supposed to be, now this explains why a TLP would this symbol would sense, right? It's using a megaphone, but it's sending a time committed version of the message. All right, and for simulation, we have to do something else, something more, which is using a programmable random oracle on top of TLPs so that it can explain things at the end. And I'm out of time, so I'll skip this. Let me go to the summary. Okay, so it should be in the, so this is that's what we call it completeness results, right? Because we cover all property-based, simulation-based, so we have possibility and impossibility results for everything. And some references, this stuff that I talked about was in Crypto 23, here's the full version. I mentioned the resource restricted cryptography paper, which is something that we published in TCC 20, which tries to capture, cryptography when you have this concrete type of efforts to, do operations like TLPs and whatnot. And finally, an advertising that was something that we have coming up in Crypto 24, where this was the classical consensus problem, right? So we look at the permissionless version of the problem. Okay, identities are not known. And recall that in all these proof of work type protocols use hash functions and the model is random oracle, which in crypto we don't like that much. So this is a first attempt to do proofs of work via no random oracles, called standard model, using something that is called fine-grained complexity. I'll be happy to talk to you about this later on. Thank you. Sorry for the time